on this computer. Okay, so let me, because we have to do some adjustments. I always have a problem. Okay. Okay, let me move. Okay, let us begin. Good morning, good afternoon. Today, we have Juan Pablo Velasquez-Rodriguez. Juan Pablo is pursuing his doctoral studies in the University of Gent. The title of his presentation is the Vladimir of Laplacian on the group on the Heisenberg group. Sorry, please proceed, Juan Pablo.
Well, okay. Nice to meet you, everybody, and thank you for the invitation. So today I'm going to talk about some rather technical aspects of the theory of pseudo-differential operators on certain classes of topological groups, and in particular, I want to talk to talk about some analog of the Vladimirov operator in the case of non-commutative groups. The motivation to talk about this matter is, for instance, the solutions to certain kind of pseudo-differential equations, I'm going to call them. For instance, well, this will be yeah, you know that a classical partial differential equation looks like something like this, or well, there is this very particular, very special equation that is somehow like a Heath equation with a certain pseudo-differential operator, and this a very standard way of studying these equations, the properties of the solutions and etc. When the functions involved are, let's say, defined in a topological group, or to make use of the Fourier analysis of the group. In this talk, we're going to consider functions and operators acting on certain topological groups with a nice Fourier transform, and by that I simply mean that in your topological group you do have some Plancherel theorem, a Plancherel formula, and that the Fourier transform is well behaved. In technical terms, that would be that. Let's say you can relax a bit these conditions, but just for the purposes of this talk, the groups are going to be locally compact, Hausdorff, unimodular, and type 1. So in those cases, you...
Juan Pablo,
yes?
Sorry, the group G must be abelian or not? It's a general group.
It can be a abelian, but it doesn't have to be.
Okay, so okay. It's in general non-commutative. Thank you.
In general, non-commutative, yes, which is actually the interesting case, because in the commutative case, all the Fourier analysis and even many aspects of the theory of pseudo-differential operators are already quite well understood, right? That was made in the past century. So yeah, actually, I want to talk today about the non-commutative case, which is a bit more complex, but also more interesting. And in the non-commutative case, something we need to remember always is that the Fourier analysis, the group Fourier analysis, this time is in terms of the unitary reducible representations of the group. So let me recall you that a representation is of a certain group is an homomorphism of the group into the space of linear transformations of a certain vector space. And in particular, when the group is abelian, those representations are unidimensional, so it's just the characters of the group. But in the non-commutative case, in general, they can be finite dimensional or infinite dimensional, but not one dimensional. Actually, you can prove that's an if and only if that the unitary representations are one dimensional only if the group is abelian. So the reason to talk about Fourier analysis when thinking about pseudo-differential equations is because, as you probably know, if you have a linear operator with an appropriate dense domain and you have some notion of Fourier transform in your group, then some interesting operators can be written in terms of a function that we call the symbol of the operator. And that looks like something like this. You have a linear operator that with the Fourier transform can be you can be regarded as the multiplication of the Fourier transform of the function for a certain other function that we call the symbol, and then you take inverse Fourier transform. Here in general, the symbol of the operator is going to be a measurable field of operators, measurable with respect to the Planck-Edel measure that we do have in the unitary dual of our group, because we are talking about groups with a nice Fourier transform. So, yeah, usually the first example of one of these groups with a nice Fourier transform will be Rn, but here we are interested in p-adic numbers, right? So our first example is going to be the additive group of the d-dimensional space over the p-adics, q sub p to the power of d. And the Fourier transform here, it's very well known, is defined as this integral against, here I'm missing a minus, against the conjugate of the characters of the group. And of course, you have a Fourier inversion formula. There is this formula here, okay, where you can reconstruct your function from your Fourier transform. As I mentioned before, for abelian groups, the unitary dual, can you see this part? Or are you seeing also the options bar?
We are seeing the options to the print. This is your PDF.
Yeah, I don't know how to move it. But,
okay.
Guess
now you have to go to full screen probably, because now we are seeing a column.
Oh yeah, but actually I don't see what's the option. This should be the option.
Okay, but now it's perfect. No, okay. Now it's okay.
So yeah, as I was mentioning, this is an abelian group. So of course, in this case, the unitary dual, or the collection of unitary reducible representations, are just the characters of the group. And in this case, they are given in terms of the p-adic fractional part function. Of course, these are representations of the group because they define homomorphisms of the group into the circle group, which can be regarded as the group of unitary operators in a one-dimensional space. And yeah, now that once you have the Fourier analysis in your group, then for an appropriated linear operator, in this particular case, by appropriated, I mean densely defined, whose domain contains the collection of locally constant functions with compact support. If you have one of those operators, you can check that at least formally, you can represent the operator in terms of an associated symbol that in this abelian case is given by this formula. Like you apply your operator T to the characters of the group, and then to the obtained result, you multiply the conjugate of the same character. In particular, there is a very special, important particular case, and is when your linear operator is translation invariant. You can check that this symbol does not depend on the variable x. It only depends on the Fourier variable. And well, how is this useful? Probably you already know how. All these methods were initially created for Rn, where differential operators via Fourier transform can be seen as pseudo-differential operators where the symbol is a polynomial. So via Fourier transform, differential operators look like taking Fourier transform, multiplying by a polynomial, and then inverse Fourier transform. And you can use that information to try to study the operator. Here in the p-adic case, we don't really have, but at least not for functions, not for complex value functions of p-adic argument, we don't have exactly differential operators, but we have the Vladimirov or the Tybalson differentiation operator, here defined, which via Fourier transform is one of those operators that can be defined in terms of the symbol. A pseudo-differential operator actually a Fourier multiplier, some authors call it, because the symbol of the operator this time does not depend on the variable x, only on the Fourier variable. And in principle, well, of course, I'm avoiding here technical details, but in principle, with this information, you do have that the equation we talked about initially, this equation for the Vladimirov operator is solvable and has a unique solution when G is in a certain appropriated function space. Actually, I think there is a paper of Wilson about this, about the appropriate Sobolev spaces for the solutions of this for this equation. So as I mentioned at the beginning, we want to upgrade this to the non-commutative case, and I'm not going to talk about compact groups. Today we're going to be focusing locally compact groups, but just to create the picture of how things work in your mind. Another example of groups with well-behaved with a nice Fourier transform is the example of compact groups. By the Peter-Weil theorem, you know that, well, first, for compact groups, you know that the representations, the unitary reducible representations of the group are finite dimensional. So you can think on your representations as matrices, because anyway, they are operators acting in finite dimensional spaces. And in terms of the matrix coefficients of these representations, like you can express any L2 function as a Fourier series. This is the content of the Peter-Weil theorem that basically tells you that the matrix entries of the unitary reducible representation form an orthonormal basis of L2. So of course your functions can be written in terms of those functions like this, where here the Fourier transform of the function this time is an operator evaluated function, but it's acting in a finite dimensional space. So usually this is simply regarded as a matrix. In the case of compact groups, or Fourier transform is matrix value is the matrix given by this expression. Okay, and in consequence, yeah, well, using this Fourier transform, we can also write linear operators in terms of a symbol. The symbol has to be a matrix value symbol, so this multiplication here makes sense. And it is given by this formula that I will ask you to keep in mind, like the conjugate of the representation composed with the operator T apply to that representation. And in particular, again, when the operator is invariant, left invariant, actually, well, you have to make a choice here, but let's say left invariant, then this symbol depends only on the Fourier variable. So in principle, the methods of the Fourier analysis in Rn can be also applied to, let's say, compact groups. And actually there is a lot of literature, especially about compact Lie groups, where you study differential operators in terms of their matrix value symbols. But again, the case I want to discuss today with you is the case, the non-compact case. And in this case, it is known that the unitary reducible representations of the group are infinite dimensional. So in this case, your representation is an homomorphism from the group to the group of unitary operators over a certain Hilbert space, with the dimension of the space being infinite, usually a separable Hilbert space. And in this case, you have to be a bit more careful with the Fourier transform. It's going to be a linear operator between infinite dimensional spaces, defined in a similar way before. And you also have a Fourier inversion formula, of course. We're going to use this Fourier transform to, again, write some interesting operators in terms of their associated symbol, but here there are more technical details in regarding which kind of operators you can effectively write as in terms of a symbol. That's not that important for the talk, because we're simply gonna consider pseudo-differential operators, which are operators initially defined in terms of a symbol. Yeah, but I want to remark the fact that for instance, in the case of compact groups, just if you have a densely defined linear operator, you can find the symbol for the operator. So it goes like both ways. If you have a symbol, you can define an operator, but also if you have an operator, you can find the symbol. As long, yeah, you don't need many conditions of the operator in this case, only that is densely defined in L2. When the group is non-compact, it's a bit more tricky to actually say which operators can have an associated symbol, but it's not going to be that important because we're going to move on to a setting where everything does work nicely, and this is the example of the Heisenberg group, which is probably the simplest of the non-commutative topological groups. There are many equivalent definitions for this group, but here simply I'm gonna call the Heisenberg group the group of matrices of this form. Well, with the natural operation, the matrix product. And for this group, you can trivially check that first, it is an analytic manifold, a 2D plus 1 analytic manifold, locally homomorphic to Q sub p power up to the power 2D plus 1. And the operations in this group are analytic functions. So that's exactly the definition of what a p-adic Lie group is. A p-adic Lie group is an analytic manifold over some non-Archimedean local field, such that the operation functions, of course, an analytic manifold with a group operation, such that the operation is also an analytic function. Lie groups. I was expecting a different. Okay, so since we are going to talk about the Fourier analysis on the group, we need to talk about the unitary representations, the unitary reducible representations of the group. And for that, I need to introduce some terminology very quickly. And it's about what kind of representations are the elements of the unitary dual of one locally compact, totally disconnected group. Because even though you have you can talk in general about representations of locally compact groups as long as they are, let's say, unimodular, Hausdorff. But there is a difference between totally disconnected groups and, let's say, connected groups. And is the kind of representation spaces you get. And there is also a difference in the representation. Well, anyway, for totally disconnected groups, what we need to know is that in the unitary dual, the elements of the unitary dual are the smooth, irreducible, smooth, admissible, irreducible unitary representations of the group. And where a smooth representation, this means that the representation applied to any vector defines a smooth function, which in the totally disconnected case means locally constant. And it is admissible if this space of vectors that are invariant over the action under the action of a certain subgroup of your big group is always finite dimensional. Because this is a remarkable difference between the compact and the non-compact case, and is for totally disconnected groups, the representations of the compact groups, compact totally disconnected groups, they all have some subgroup of the big group where they act trivially, where they are equal exactly to the identity. But if the group is non-compact, the unitary irreducible representations cannot have that property. They can act as the identity only in a finite dimensional space. So as usual, we're gonna denote the unitary dual of the group as the collection of algebraically reducible admissible representations on the group, and oh well, this is, yeah, I'm not gonna need this. So now let's talk about the unitary dual of the Heisenberg group. The unitary representations of this group are something very well known, especially thanks to the Kirillov orbit method. It doesn't matter over which field you consider this same matrix group that I defined previously, the Heisenberg group. The way of obtaining the unitary irreducible representations is the same. So in a very similar way as for the usual Heisenberg group over the real numbers, here in the p-adic case, we have two different kinds of representations for the Heisenberg group, and they look exactly the same. First, you have some representations that restricted to the center are trivial representations, so that they define representations of this quotient group that is actually isomorphic to q sub p power 2d, which is an abelian group. So the representations, this kind of the representation have again the form of the character of an abelian group. And in the second case, the representations which are not trivial in the center, since the center is an abelian group, when restricted to the center, they must have this form, a character of an abelian group. And those are the representations that actually, by induction gives you the unitary reducible representations of the group. Well, more like the generic ones. Because something to remark here, I was forgetting, sorry, is that once you have the Planck-Gérel measure in the unitary dual of the Heisenberg group, these unidimensional representations will have measure 0, and these are going to be the representations that actually count in the Planck-Gérel formula. So for all practical purposes, these representations, which are the p-adic Schrödinger representations, are the elements of the unitary dual that we are actually going to need. And yeah, one can check that these are all the representations of the group here. I refer you to the reference for more details. Yeah, now you can see it. So the Fourier transform in this group, now that we know how the representations are, it's going to take this form when applied to a vector of the representation space, which in this case is going to be the space L2, a function in the space L2, acts in this way. And this integral can be rewritten just with some change of variables. Again, it's probably showing the Barak. Okay, this integral can be rewritten so that the Fourier transform looks like an integral operator with a kernel that is given by the Fourier transform in Q sub p of your function f. Recall that with the Heisenberg group, or in general with any p-adic Lie group, you can, when the group is nilpotent, you can identify your group with Rn and a certain operation. Sorry, with Q sub p n with some non-commutative operation. So you can you can think on your functions on the group in two different ways, as a function in Q sub p or as a function in the group. but the function in the group will be like the same function composed with the exponential map. So yeah, in this case, the group Fourier transform applied to an element of the representation space takes the form of an integral operator, where the integral kernel of the operator is given in terms of the Fourier transform in Q sub p of your function f, and that is going to be important because, for instance, if we restrict our attention to functions that are locally constant in the Heisenberg group, those actually correspond to functions that will be locally constant also in Q sub p, and therefore this kernel is the Fourier transform of a locally constant function with compact support.
Sorry,
Yeah,
Juan
there is a
Pablo.
question?
Yes, yes. Could you please come back to the previous slide? Could you please,
This?
yes, could you please say something about the bilinear form? It seems that there is a bilinear form in the last integral. Parentheses psi, comma, lambda, then there is another comma, lambda. This is a bilinear, you have a bilinear form. Or what is the meaning of that expression?
Oh, but here I'm not thinking about that really.
What is the meaning of the expression? Because I do not understand this expression.
Oh, well, simply this time your Fourier transform, it's going to be an operator in the representation space given by this expression, this integral.
No, but I'm asking about
now,
in the last integral.
Now
there is
you can rewrite this integral. Yeah, if you replace here your f for the Fourier inversion formula, but not in the group, in Q sub p. Okay, you just, yeah, if you want to jump from this line to this line, you only need to replace f with the Fourier inversion formula in Q sub p, and yeah, do the calculations, you get the integral, and then you can rewrite this like this integral operator.
So basically the psi, comma, lambda are the arguments of the Fourier transform.
Yes.
Oh, okay. Yeah, sorry. I was thinking something else. Yeah, yes. Okay. Thank you.
Oh, yes. So this is a function. Yeah, this is a function in the Heisenberg group, but you can also think about it like a function in Q sub p 2d plus 1, right? And that function has a Fourier transform in this group. You can replace this function for that expression, the Fourier inversion formula in Q sub p 2d plus 1. And yeah, well, some of the exponentials are gonna disappear here, and you're gonna obtain, after a change of variable, the third line here. So, okay. Well,
thank you.
Well, what I'm saying, it's simply that in this case, the Fourier transform is a Hilbert-Schmidt operator, actually, or in principle just an integral operator, but you can also check that it is Hilbert-Schmidt. And in the way we rewrite things here, this is the Hilbert-Schmidt kernel of the operator. So we can easily obtain the Hilbert-Schmidt norm of this operator and check the Planck formula actually holds when you put the right measure here in the unitary dual. And here the right measure, this is going to be your Planck measure. Yeah, the absolute value of lambda of the power d times d lambda. So with this measure, again, we have a Fourier inversion formula on the group, and we're going to use that Fourier inversion formula to try to write some interesting operators in terms of some associated symbol, which, again, I want to remark in this case, have to be operators acting in the representation space, which for the representations of the Heisenberg group, again, it's for every representation is actually the same space. It's just the space L2 over the p-adix. So yeah, once again, we can, as for compact groups, or as for the case of Q sub p, one can write some linear operators in terms of an associated symbol which is given as for the compact groups with the same formula, just the adjoint of the representation times or compose, because these are actual operators with the operator applied to the representation. But it's actually also equal to the operator applied to the representation and then evaluated in the origin. And that actually coincides with the Fourier transform of the convolution kernel of your linear operator. So an advantage of this symbolic representation is that in the same way in Q sub P, you can very easily, at least in principle, at least formally, write the solution to one. So the differential equation using the Fourier transform. In this case, in the non-commutative case, you can apply the same ideas, and as long as for example, when you have an invariant operator, so the symbol of the operator only depends on the Fourier variable, and the inverses are bounded operator, you can, in principle, compute or define a formal fundamental solution for your operator. You can have an inverse. You can solve the equation associated to the operator. And of course, I'm just talking about the ideas because there are many technical details that one needs to check. But it's the same idea from Q sub P in general for abelian groups. Just that this time we're going to have to deal with operator valued Fourier transform and symbols. But at least for some operators, that's something doable. And I want to talk about one of the operators where you can actually apply all the same arguments because you have all the required tools. And that is something called, by some authors, the Vladimir of Laplacian. I actually haven't seen a lot of literature about this operator, mostly about the table sum operator. But this is an operator that initially was studied by Vladimirov in the case where alpha is equal to. But recently, well, not that recently, but there is also a paper of Grigorian studying this operator. And well, yeah, there are a couple more in the literature. Probably you know the Vladimir operator in the p-adic numbers, and you know one way to generalize it to the multi-dimensional case, which is the table sum operator. But there is an alternative way to somehow generalize your Vladimir operator from the one-dimensional case to the multi-dimensional case, and it's instead of taking convolution with the p-adic metric, let's say, that is what you do with the table sum operator. You take your Vladimir operator in every variable, in every direction. Something similar is what we are going to do here, and it's what I'm calling here the Vladimir of Laplacian. This operator is defined in this way. And it's kind of like taking the one-dimensional Vladimirov operator in the direction of each one of the generators of the Lie algebra associated to the group. Yeah, actually, I'm sorry. I think I jumped one of the. Yeah, I think. Oh yeah, I forgot to put the Lie algebra, or something happened with the order of the beamer. But anyway, let me mention it. And is as you know, Lie groups have an associated Lie algebra that can be identified with the tangent space of the Lie group as a manifold in the origin. In the case of the Heisenberg group, that Lie algebra is actually generated by the commutation relations of 2 times d, let's say, vectors whose, oh yeah, actually, let me check if maybe it's later. Oh no. Okay. Anyway, the Heisenberg Lie algebra is generated by 2D vectors and their commutation relationships, where the relationships is like xj, the commutator of xj and x, let's say I, is equal to 0 unless j and I are equal, and when they are equal, the commutator is equal to z, which is like the generator of the center of the algebra.
So, Juan Pablo, so xj, yj, and z are matrices with p-adic entries?
No. Oh, yes. Sorry. Yeah. But if you're thinking on your group as a matrix group, right? And the Lie algebra is also a matrix group, and yes.
So what is the meaning of the exponential t xj and then the inverse?
Oh, that's the exponential map in the Heisenberg group. It's
Yes,
just
but
that
this
I'm missing one
map,
of my.
yes,
Sorry,
yes. No, but I'm thinking this exponential map gives a p-adic value. Is a p-adic value exponential or a real value exponential? Because oh no. Oh, one more time. Yes, is a p-adic value exponential. The problem is
the
that
matrix
you have
exponential.
too many parameters. Yes, inside of the parentheses you have x, y, and z times this, and really isn't.
Oh yes.
Yes.
This is a point in the Heisenberg group, right?
Yes.
This is like operation in the
yes.
Heisenberg group, the exponential image of this element,
which is a p-adic value. It's a p-adic value function, and then when you multiply by the p-adic variables, everything. So okay, yes,
yes. Sorry, here this exponential is the matrix exponential, because that's what I was saying. I am missing a frame. I don't know if Overleaf didn't compile it, but yeah, I had a frame about the Lie algebra just after the Lie group, but it's not showing it here. But anyway, any Lie group has an associated Lie algebra and an exponential map that, since this time we're talking about matrix Lie groups, is simply the exponential map of matrices, right? And there is no problems of convergence with that exponential map here, because the group we are considering is nilpotent. So actually, our Heisenberg group, as we define it here, can be considered exactly equal as the exponential image of its associated Lie algebra, and do it with an operation that would be the Baker-Hausdorff-Campbell operation. And yeah, you can even think about this product here as that operation. But anyway, I don't know if you can recognize it, but this is kind of like taking partial derivative partial Vladimir operator in the directions of x, y, and z. And well, these operators have some interesting properties, like being the first one, you can check they are homogeneous after defining appropriately dilations of the group. But anyway, the most important thing for us right now, it's going to be this. What are the symbols of the operators? And it turns out that when you take this, let's say, partial Vladimir operator in the direction of the x's, what you obtain in the representation space is like applying Vladimir operator with the same order, alpha, in the different directions of your functions in the representation space. Recall that this is a function in Q sub p d, right? So that function you can for that function you can apply the Vladimir operator in any of the d different directions, in the direction of u sub 1, u sub 2, etc. When you take in the Heisenberg group the Vladimir operator one-dimensional in the direction of the y's, what you obtain in the representation space is like a multiplication operator by the p-adic absolute value. Oh, sorry, here you should be seeing a p.
Oh, Juan Pablo, sorry, a comment. Because you are working in manifold, these partial derivatives have a standard meaning, but it seems that you are using the symbol partial alpha sub x in two different ways. in the first formula, when you say equal partial alpha sub u j
Yes.
phi u, then in this expression, this is a Vladimirov operator acting on a test function or something like that.
Yes.
I strongly suggest use a different notation for the Vladimir, for instance, capital B alpha, something like that, because here in differential geometry, these partials, these functions, these symbols have a very standard.
Oh yeah. Then
so it is quite confusing. You see, because this is these are the generators of the tangent space. I mean, something like the generators of the tangent space. You see.
Exactly. The xj's, yj's, and the z are the generators of the tangent space.
Tangent space. So okay, but I think that.
Sorry, then let me do the remark that here I'm using this notation, but there is no relation between. Actually that's something important to notice. These operators are like, let's say, Vladimirov, one-dimensional Vladimirov operator in the direction of a certain element of the Lie algebra. But that has nothing to do with what are actually defined as differential operators or in general p-adic Lie groups, because there is actually no correspondence.
Exactly. So, we are talking about two completely different worlds.
Yes. So, for instance, these, let's call them directional Vladimirov operators, do not carry the Lie algebra structure. That's a very
like
big difference between
case,
real Lie groups. Exactly. In the classical case, it's actually a theorem that there is a one-to-one correspondence between derivations, right, and directions in your manifold.
Exactly.
But here, this is not a derivative in the usual sense. It's just the Vladimirov operator, which somehow can be regarded as the derivative or the analog of derivative in this sense, but it's not related with the concepts you use in, let's say, geometry. Still, something I want to remark today is how similar this operator, in particular the Vladimir of Laplacian, turns out to be when you compare it with, for instance, a sub-Laplacian in graded Lie groups. In particular, in the Heisenberg group, the sub-Laplacian is a differential operator. You also have a very similar Fourier analysis in the real Heisenberg group, and when you go and check at the symbol of the sub-Laplacian, what you obtain is the harmonic oscillator. The sub-Laplacian is a differential operator in the Heisenberg group, the usual one, the real, that can be expressed as a pseudo-differential operator with the Fourier analysis of the group. And when you do that and you check what the symbol is in each representation space, it acts as the harmonic oscillator. Here you kind of get, well, no, that's not an harmonic oscillator. It's something that Vladimirov itself called a Schrödinger type operator, something like Vladimirov operator plus multiplication by a certain potential. And fortunately, Vladimirov studied already the properties of these operators in Q sub p. So for instance, that this is the next theorem. We know we have some information about the eigenvalues of this operator. We know that it is actually self-adjoint, or at least you can extend it to a self-adjoint operator, right? The minimum eigenvalue exists and it's something positive, so your operator is going to be invertible, right? And because it is self-adjoint, it has associated to it a functional calculus, the functional calculus for self-adjoint operators. And why is that important? Yeah, let me do here a small parenthesis, and it's in real Lie groups, a very important class of operators that you study are called Rockland operators. Rockland operators are simply homogeneous hypoelliptic operators on graded, let's say, Lie groups. These operators are remarkable because actually the existence of a parametrics or a fundamental solution for this operator it's very well understood already. There is something called the Rockline Condition, and I'm forgetting the name of the theorem right now. Yeah, there is this theorem. Sorry, I forget the names of the theorem. That simply tells you that the hypoellipticity, which is a very important property of the differential operators, it's characterized completely in terms of the Fourier analysis of the group of the symbol of the operator, and it's equivalent to a condition that is called the Rogueline Condition, which simply says that yeah, your operator satisfies the Rockland condition if and only if it is injective in every representation space. And here, this operator that we obtain in every representation space, it's gonna be injective. And actually, since it is positive and self-adjoint, and you have a nice functional calculus for it, you also have a nice calculus for the Vladimir of Laplacian in the Heisenberg group. So that from the properties of the symbol, you can deduce that your operator, your initial operator it also has some very nice properties like the self-adjointness, right? And more important, the existence of a functional calculus for this operator. As a consequence of that existence of the functional calculus, you can actually obtain the heat semigroup and the heat kernel associated to your operator, and from the heat kernel, as you know, as long as some technical conditions are satisfied, you can obtain a fundamental solution for the operator. So yeah, now I want to take some time to discuss these 3 questions. Yeah, because these are questions that are in my mind, and maybe someone from this seminar that actually has some idea on how to think about this. And well, this analysis I show you here for the Vladimir of Laplacian, it's something that doesn't require many ingredients to be carried out, just as for Rockland operators in Lie groups. Actually, that's the reason why Rockland operators are that special, because talking in general about differential operator is quite complicated. But if you have some extra conditions, some extra properties, hypotheses, then things are more manageable. For instance, Rockland operators are, apart from differential operators, are, oh, sorry, I was forgetting to mention these invariant operators in the groups, translation invariant. They are also homogeneous. And just those 2 conditions simplify a lot of things. It's the same here. In general, yeah, considering operators, even pseudo-differential operators, even if you know the symbol and the symbol is, let's say, a well-behaved symbol, it's not that trivial to obtain results, like, for instance, the existence of a fundamental solution of the operator, or knowing very well for which kind of functions the fundamental solution can actually exist, or yeah, there are in general many complications, but this is an example of an operator on p-adic Lie groups where you also have some properties like for the Rockland operators, the invariance. These operators are left invariant operators, and also they have a certain condition of homogeneity that that make possible, for instance, the construction of a fundamental solution. And and well, there are many other related constructions, like related to the function spaces associated to these operators, and etc. The only thing you really need to find a fundamental solution for these operators is a theorem like this one of Vladimirov. You only need to know that in each representation space your operator is invertible, and if apart from that you have extra conditions like the self-adjoinance, then you do actually have a heat kernel with a very nice properties that you can prove just by using the homogeneity of the operator. So the critical step that is missing here, it's something that is known for real Lie groups, but yeah, for operators on p-adic groups, I don't see what will be the method. Is this estimate number 4 of the heat kernel that basically tells you that the heat kernel, it's kind of yet in the variable t, it is goes asymptotically, or it goes asymptotically like t at the power minus the homogeneous dimension of the group over the degree of the operator. Because if you have that, then you have this conclusion that for alpha between 0 and the homogeneous dimension of the group, you do have a fundamental solution, and it can be fine in this way, and it has some very nice properties. It is known that this estimate of that kind holds for Rockland operators, and the method of proving that only needs to use the homogeneity of the operator and the Rockline condition. But here in these groups, well, I haven't seen any authors talking about what apoellipticity will mean in this scenario, because at least in the real case, it is related to, yeah, somehow it's related to the existence of a fundamental of a functional calculus, and therefore of a fundamental solution for the operator. So yeah, I'm trying to think about these questions and see what other parallels are between this kind of operators defined in terms of the Vladimirov operators, and some classes of differential operators like the Rockland operators. What else do I want to say? Well, something I'm interested in now, it's to check whether the function spaces defined by this Vladimir of Laplacian actually have some similar properties to the Sobolev spaces in real Lie groups. And yeah, it's something I am trying to check, is whether homogeneous operators of the same degree, let's say, who satisfy a condition like the Rockline condition, like the condition this Vladimir of Laplacian satisfies, the invertibility in each representation space and the homogeneity. If the Sobolev spaces defined in terms of those of other homogeneous operators of the same degree with the same conditions are the same, or yeah, because that's something kind of important in the case of real Lie groups. But yeah, there are many questions related to this kind of operators that I would like to solve. So if any of you want to discuss anytime, just let me know. Okay, I think that's what I wanted to say for today. Well, actually, there are other things to mention, but maybe in a next opportunity.
Okay, Juan Pablo, thank you very much for your nice presentation. Are there comments or suggestions from the audience? Okay, let me make some comments. I do believe that the study of pseudo-differential operator or pseudo-differential operators on p-adic manifold is important, because this is connected with the classical Atiyah index cathodic index theorem. Okay, in general, we know that, or we expect that the spectra of the spectrum of an operator defined on a manifold must be controlled by the geometry of the manifold. So it will be very interesting to have similar results in the p-adic framework. Okay. Now, it is also interesting. I mean, I strongly suggest considering the sublevel spaces in this framework. Okay. There are some results about sublevel spaces on general metric groups that you can probably use in this. I can give you the reference later. Okay. Okay. Are there more comments or questions from the audience? Well, let me stop the recording.